All right. So we're going to start to sort of turn the corner here. This chapter has been about integration techniques. And essentially we've done, what, 4 different techniques, 5 different techniques. We started with integration by parts. Then we looked at a variety of ways to integrate trig functions. Then we looked at trig substitution. Then we looked at partial fractions. So that was 4 different techniques. And then the last time we looked at using CAS and tables to do the integration when other methods don't work. So today we're going to sort of move away from calculating integrals directly and coming up with antiderivatives to approximating integrals using approximation techniques. And then next time we'll go back to calculating integrals, but in the sense of what we call an improper integral. So those are our last 2 sections for chapter 3, and it'll be up through that material on improper integrals that we have on our midterm. So that's sort of where we'll be. That midterm, that means that that will include all of the applications and other things from that first chapter, along with all the integration techniques from this chapter. And you'll have, as we mentioned last time, at least a few days, I think it's in the schedule from the 26th to the 29th or something like that, to work on the midterm, and then you'll just turn it in and upload it to the assignments folder in D2L. So any questions about that? I'm sure you might have more once you have more details. All right, so let's take a look.
Good morning.
Morning. Did you also have trouble getting in, Gabe?
Yeah.
Merrick had a little trouble too.
I think it's been, I don't know, it's either my home computer or my, because it's been happening a lot lately with Zoom, but I think I told you, I just switched over to my Zoom, to my home computer, and because my other one broke. What?
You did, yeah, you did mention that.
Yeah, so that might be the reason why, because maybe it's just, this one's a lot slower, but
okay,
that could be the reason why, or maybe it's just because of Zoom. I don't know.
Yeah, they might be getting bogged down too with number of users and everything and having maybe some bandwidth issues. It's hard to say.
Right.
Okay, so let's go ahead and get started. We're gonna go ahead and just double checking the chat over here. We're gonna go ahead and start looking at approximation techniques. So I am gonna try, let's just start with the whiteboard. Okay, so you should have my whiteboard, and I'll plug this because it's just easier that way. Okay, so with approximation techniques, we're really going to go back to what we did when we first started integration with Riemann sums. So we've actually already done some approximation techniques for integrals when we set up how the definite integral is defined. So Riemann sums, we're really using rectangles in order to approximate integrals. So as an example, we might, and let's just start with one that's not really too awfully difficult, but that at least has some approximation necessity to it. Let's suppose we wanted to integrate the natural log of x. And if we're approximating an integral, it must be a definite integral, right? That's the only time we're calculating a number. So let's calculate the integral of natural log of x from 1 to, how about 5? So we want to get an idea of what the value of this integral is. And if we think about it in terms of, oh, that's terrible looking, vertical axis, that's slightly better. If we think about the graph of the natural log function, remember it crosses the x-axis at 1, 0, increases left to right, but pretty slowly. And so 2, 3, 4, 5. And that integral, remember, represents the area under the curve from 1 to 5. So that's really what we're trying to approximate. And we did this back when we started setting up the definite integral and how that works by saying, you know what, we could actually just try to sort of embed rectangles in here. And we did these a few ways. Do you guys remember doing that back in Calc 1 or no? Who remembers using rectangles to approximate?
I do.
Eric says yes, and someone else says Aaron E says yes. Okay, so, and we could do this with any number of rectangles. For example, if we wanted to be sort of really crazy, we could say, you know what, we're just gonna use one rectangle, and we're gonna make that rectangle go from all the way from 1 to 5. That would be a pretty bad approximation. It would be much larger than the actual value of that area. We could also say, you know what, we want to use more rectangles and maybe we want to place them differently. So I'm going to actually just undo that so that that's not hanging around for us. We could do, let's go 4 rectangles, and we could place them so that the height of the rectangle is determined by the right end of the interval. So there are 4 rectangles, and we've got an overestimation, but it's not nearly as poor as the last one that I drew. And in order to figure out the area of each of those rectangles, we just need to know their width and their height. So how does this work? Well, in this case, with these right endpoints, we could say that the area is approximately width times height, width times height, width times height, width times height, 4 times. And to get the heights, I just need to know the y values on that curve. And remember, the curve that I used was y equals natural log of x. So for my first rectangle, how wide is it? Actually, for all of my rectangles, since I evenly spaced them, how wide are they?
1.
1. Okay. I was trying to make the numbers fairly nice. So first rectangle is 1 unit high, and it is how tall? As an exact number.
ln x.
ln of x. And what's the x value for the first rectangle?
X.
What's the x value for the first rectangle?
0. Oh, the x value? Sorry, 1.
Nope. I'm using right-hand endpoints.
So, 2. No, never mind, 2.
2. So the height of that rectangle is natural log of 2. And the height of the next rectangle is natural log of 3. And the height of the next rectangle is natural log of 4. And finally, the height of the last rectangle, oops, I forgot my 1, is natural log of 5. So another way to say this is 1 times the sum natural log 2 plus natural log 3 plus natural log 4 plus natural log 5. And those values are just my y values, or the function values, the f of x values. And we could go ahead and calculate that. Does anybody have a calculator out where they can add ln2, ln3, ln?
Yeah, I can.
All right. Thank you. And then just maybe like 3 places after the decimal will be good. think I left my calculator somewhere else.
4.787.
4.787.
Oh, wait. I did the 1 too. Wait. That'll just be 0, so never mind. It's fine, yeah.
Yeah, that would be okay. Now that's sort of interesting that you did the 1 also. So if you did want to use, so that was with right hand endpoints.
Well, I just did it on accident. I didn't mean to type it in my calculator.
Understand.
Okay.
We did that one with right endpoints. If we had used left endpoints, it would have looked like this. So left endpoint, left endpoint, left endpoint, left endpoint. And notice that the first rectangle actually has 0 as its height, the natural log of 1. So you're right, that contributed nothing. But then the second rectangle is here, the third one is here, the fourth one is here. And in this case, because the graph is concave down, these left rectangles are going to be an underestimate. So we could do this again and say area is approximately 1 times ln1 plus 1 times ln2 plus 1 times ln3 plus 1 times ln4. And since this number is 0, we can actually get this value by taking our last answer and subtracting natural log of 5. So will you do that for me?
Subtract natural log of 5.
Yeah.
Okay.
From the 4.787.
3.178. 80, but so just 3.178.
Okay, so that is left endpoints.
Is it?
It is. It should be natural log 1 plus natural log 2 plus natural log 3 plus natural log 4, if you calculated correctly.
Yeah, I did calculate correctly, but then you told me to subtract ln 5.
Right, because you got the ln5 from using right endpoints.
Oh yeah. Okay.
So yeah, they just, all the rectangles shifted over 1.
So you really only had to do 3 calculations. Well, 3. You only had to add 3 numbers together to get left-hand endpoints.
Correct, because one of the you actually added 4 numbers, but one of them was 0.
Right. So technically, in the calculator, if you knew that ln of 1 was 0, then you didn't have to type that in.
Correct.
Okay. Cool.
Yes.
Thank you.
Okay, so we can kind of see that in this scenario, one endpoint gives us something too big, the other endpoint gives us something too small, and often it's nice to actually go somewhere in between, because we can in reality use any x value in each interval to come up with a Riemann sum. It's just convenient, at least when we're setting up our integration and when we came up with how we integrate functions using the definite integral, to use endpoints. Now, if we're actually trying to approximate, the endpoints aren't necessarily the greatest. And so where could we find maybe in between points that would generally work better, do you think?
0.5. Or
Yeah,
1.5, I mean, sorry. 1.5, 2.5, 3.5, 4.5.
Exactly. And those would be a midpoint approximation.
Yep.
So if we use a midpoint approximation, we use these guys, and our rectangles count a little bit too much, but then a little bit not enough, and there's sort of a balance, so hopefully this is closer. So
could you ever take the average of the three?
That you could, that would be another way to approximate, right?
The average of the right and left and midpoint?
Yeah, or maybe you just average the left and right.
Right, okay. I was just wondering if that could get,
I mean,
if you average left and right, would you get the mid?
That would be yet another approximation technique.
Okay, gotcha.
So here's the third one. And here's the fourth one. And let's see, so what would this look like? Area is approximately, they're still all 1 unit wide. So I think you guys would be okay if I factor out that width, the 1. And then I'm gonna add natural log 1.5
Your answer when you're ready.
natural log 2.5, natural log 3.5, and natural log 4.5. And you have that calculation for me?
Whenever you're ready.
Go for it.
All right. 3.057.
Uh-oh, something's wrong.
I did something wrong?
I don't know. Somewhere in these calculations, something's wrong. And here's how I know that. I'm going to write down the number you just said.
I'm sorry. It's 4.0785 or 4.079.
Okay. Do you see
No,
where I knew that was wrong?
because that was smaller than both
The
of them.
other
Yeah.
two. Yeah.
Yep. I multiplied the L in 2.5 and 3.5. I didn't add it.
Okay. So tell me that
Yep.
again.
4.079.
Okay.
Yep. And that should be correct.
Okay. So that's using midpoints.
Yep. I did 1.5, 2.5, 3.5, 3.5, and 4.5.
Okay. Now let's go back and let's calculate the integral of ln x dx. So I'm just going to pull up Mathematica. Do this. So we want to integrate natural log of x
I got the answer when you're ready.
from 1 to 5. Okay. And oh, I know what's wrong. Did you get 4.047?
Yep.
So my calculator says 4.04719. And that midpoint approximation was pretty decent with just 4 rectangles. The others, not so much. So midpoint or rectangles are just one way to do an approximation. And it's usually pretty straightforward. We can use left endpoints, right endpoints, or midpoints. Okay. So that's the rectangle approach. Now, there's nothing really wonderful though about rectangles, because you can see, especially with those blue rectangles, there's often a lot that's either left out or a lot that's counted that shouldn't be. So it would be nice if we could use different shapes. And there are lots of different options that we can go with. So the next one we're going to take a peek at is what we call the trapezoidal rule. Oops. E. So using trapezoids to approximate. Okay. So who remembers the formula for the area of a trapezoid? That's on your list of things to memorize. Not really. Who knows what a trapezoid is? Maybe that's
I do.
What is a trapezoid?
Trapezoid's like a square, but it's has like it's like kind of like a square, but it's a lot wider. Like the top's a lot wider than the bottom.
Like a square but wider. So that, to me, that's a rectangle.
Okay, like the top is a lot like longer than the bottom. In the base.
Oh, okay. So you want me to make that the top longer and the bottom shorter?
Yeah.
It's not a very straight bottom. Okay.
Yeah.
A triangle without a point. Oh, I like that, Merrick. So a triangle, so you just sort of chopped off the point. I chopped it off from the bottom in this case. Yes, Aaron Engler, that is correct, with parentheses around the A plus B. And without the 4 there. I think that was just a little typo. So area of a trapezoid is and there are a couple of ways that we can write this. Aaron wrote it as A plus B over 2 times the height. So you take the height of the trapezoid and you multiply it by the average value of the two bases. A lot of times this is not, so Aaron was calling these A and B. A lot of times they will label those as, and I'm going to turn my trapezoid the other way. They will label these as base 1 and base 2. So we could write that as height times base 1 plus base 2 over 2. And the height is that perpendicular distance between the two bases. And it's easy to verify that this formula works. It's essentially taking the area of that rectangle on the inside and then adding the two areas of the triangles on the ends, and you will come up with this. Okay, so there's the area of a trapezoid. Before I take your question, Gabe, I do want to remind you that we can place trapezoids anywhere we want. And the requirement for a trapezoid is that you have two parallel sides. So it's a four-sided figure, a four-sided geometric figure. It has to be, it's got to be a convex figure, which means you don't have any angles coming, swooping into the inside. And two sides have to be parallel. So two sides must be parallel. That means every parallelogram is also a trapezoid. Every rectangle is also a trapezoid because it has two parallel sides. Every square is also a trapezoid. So it's just generalizing the picture a little bit. And that means that this has to be just as good of an approximation as rectangles, but in many cases will be better. Go ahead with your question. I think that was it.
Yep. Someone else might have a question too. But I was asking if that first trapezoid we drew was the inverse it was like inversed.
Well, we could argue about that. So
oh, okay. Well, I don't want to argue.
I mean, it's just in our normal picture of a trapezoid, it's kind of upside down, right? But it's still a trapezoid. It's just like this is a triangle. And if I like upside down it, that's still a triangle. It's not really an upside down triangle. It's just a triangle.
So it's preference. So, I mean, I could call that a regular triangle, or I could call that a sideways triangle or upside down. It's preference.
Right. It really doesn't matter which way that trapezoid is oriented on the page. And that's actually a good question, because the trapezoids that we're going to look at are actually going to be sideways. So picture this for your trapezoid.
But I could call that a regular trapezoid.
and it is a regular trapezoid. Notice that the two bases are vertical. And the height is the distance between the two bases.
But that's straight up and down though. That base.
It doesn't matter. It's still a trapezoid because it has two parallel sides.
Oh, okay.
Right?
So the square trapezoid?
Still find its area by taking the sum of the bases and dividing by 2 and then multiplying by the height.
Wait, so it's a square trapezoid?
I just said that a few minutes ago.
Oh, my bad.
Yes, a square is a trapezoid. It's a very special case of a trapezoid, and we probably wouldn't use the trapezoid formula to find the area because that would be overcomplicating matters, right? You're not agreeing with me. Okay, so that last picture that I drew is going to be an important one for us because most of the trapezoids that we look at are going to have a shape very similar to that. Let's go back now to our natural log function. Remember, we were trying to estimate the integral of ln x dx from 1 to 5. This picture, the nice thing this time is we only have to do this one time. We're not going to do left end, right end, and midpoint because those aren't going to exist when we don't have rectangles. So we're going 1, 2, 3, 4, 5. 1, and we slowly increase. Something like that. Not drawn to scale on the y-axis, but sort of a rough picture of what we've got going on. So 1, 2, 3, 4 subintervals again. And we can do any number of subintervals. I like to do 4 because it's enough to show you what's going on, but not so many that we get bogged down in too many calculations. Now we're going to draw a trapezoid in each of those. So I'm going to start actually in the second one because it's a little prettier than the first one. That's a trapezoid. That's a trapezoid. That's a trapezoid. Notice that this means we don't leave out any of the y values. We do have to use this last section. And in theory, that's a trapezoid. You have to go with me on it. One of the bases just happens to be 0, so it collapses down to a triangle. So we have 4 trapezoids, and if we want to compute the area, we're just going to add all of the areas of the trapezoids. So it's going to look a little messy at first, but then we're going to clean it up quite a bit. All right, so I'm going to start with the first one. We've got a 1/2 times the height. Now, keep in mind, the height of the trapezoid is actually this distance. There's the height. The height is the delta x value. And in this case, the height is 1. And the 2 bases are the 2 y values. So the 2 bases are this y value and this y value. So 0, which is really ln1, and ln2. And I should say is approximately equal to. And then I'm going to do that for each of my trapezoids. The second one is going to be 1/2 times 1 times ln2 plus ln3. The third one's going to be 1/2 times 1 times ln3 plus ln4. And finally, 1/2 times 1 times ln4 plus ln5. Now, I could go through and calculate that exactly as it's written, but let's make our calculation a little bit simpler. Every one of those terms has a factor of 1/2 times 1 in it. So I'm going to factor that out. 1/2 times 1. And I know I don't need to write the 1 there, but I'm leaving it there for purposes of identifying what it is. And then left, when I factor that out, I see ln1. I see 2 times ln2. I see 2 times ln3, 2 times ln4, and then finally natural log of 5. Oops, and it should be a square bracket, since I used a square bracket on the left. So notice that inside those brackets, all of my y values appear at least once, but the middle y values appear twice. And that's because they were in 2 different trapezoids. In other words, this side, we'll make it a little brighter, was in the first trapezoid and the second trapezoid. This side was in the second and third. This side was in the third and fourth. Whereas the left and the right ends were only in 1 trapezoid each. So they only appear once, whereas all the others get a coefficient of 2 because they appeared twice. So that's going to show up in our formula for the trapezoidal rule, which is going to look something like this. That area is approximately 1/2. That came from the formula for the area of a trapezoid. The 1 was the height, or the delta x. And in parentheses, we've got our y values. So if I number these, I'm going to call the first one y sub 0. And then I have 2 times y sub 1, 2 times y sub 2, 2 times y sub 3, and then finally y sub 4. The end values only appear once. And the middle ones are all multiplied by 2. So that's our trapezoidal rule. And that means we need to add those numbers together, multiply by 1/2, and we come up with our approximation. Let's see. So I get log of 1 plus 2 times log of 2 plus 2 times log of 3, 2 times log of 4, plus the log of 5. And then I need to multiply all of that by 1/2. All right, I get 3.98277. Did anybody calculate that along with me? $3.983. Yes? No? Still calculating? What's happening out there? Caitlin, Aaron, Merrick, Gabe, we good? Give me a yes in the chat. Okay, thank you.
I'm still typing it in my calculator.
I know that was a long, so you can imagine typing these in on your calculator.
I couldn't unmute for some reason, so, but mine, I got 4.022. Maybe I added it. I had to have added it wrong somewhere.
So were you computing with the natural log function?
Yeah. Let me double check just to be sure real quick. Okay.
Also got the same thing as you, the 3.9823.
Okay, all right.
Oh, so you got what you got? Okay, cool.
Thanks for verifying, Caitlin.
Yeah, I mean, I must have done something wrong then.
All right, so that's sort of how the trapezoidal rule works, and it really doesn't matter how complicated the function is, because what you're going to do is you're going to use the function y value in order to just calculate that height each time. And by height, those are the bases. So the formula that you see at the bottom of the page here in blue is sort of the special case formula for trapezoidal rule when there are four regions that you're using. If you used 8 regions, you would just have the endpoints, and then you'd have the others in the middle all multiplied by 2. You just have more terms in there. So you can kind of see that if you do a ton of these without a calculator, they can get very tedious, especially if you have lots and lots of subintervals. You shouldn't have to do that too much. All right, so that's the trapezoidal rule. The trapezoidal rule is nice because it allows us to have this sort of slanted idea going on, where we have less of the error than we do with the rectangle, where we go straight across and then we get these little almost triangular looking pieces that either don't get counted or that get counted too much. So what would be really nice is if instead of using something with a straight line segment, we could somehow curve our approximating figure. So tell me what you think of when you think of the simplest mathematical kind of function that has a curve to it instead of just a straight line segment.
Square root.
Okay, you're on the right track. So the square root is relatively nice, but maybe not so easy to calculate with.
ln then?
Nope, simpler than that.
It would be
Half a
x
parabola or
squared?
circle?
Caitlin?
Would it be x squared?
X squared, yeah. So it's essentially the square root function, but the inverse of the square root function.
Oh yeah, yep.
It's pretty easy to square a number, and it's a relatively simple expression in terms of what it looks like. And it's also something that we're able to figure out a formula for. So and this is called Simpson's rule. So Simpson's rule uses parabolas to approximate. Now, in order to determine a parabola, how many points do you need? In other words, if I give you 1 point, can you draw just one parabola through that point, or can you draw lots of parabolas through that point?
Lots.
Lots of them. Okay, if I give you 2 points, can you draw just one parabola through those 2 points, or many parabolas again through those 2 points?
Still many.
Still many, because if we think about 2 points, I'll just put 2 here. I could draw one parabola that goes this way. I could draw another one that goes this way. I've got lots of choices. So how many points do I need to determine a parabola? What if I go up to 3? 1 point, 2 points, 3 points. 3 nonlinear points. If they were all in a straight line, I'd have some trouble. 3 nonlinear points, there's just going to be 1 parabola that fits through them. The one way to think about this is that, remember, parabolas have a form that looks like y equals ax squared plus bx plus c, right? And there are 3 parameters in here, the a, the b, and the c. So we need 3 points in order to determine a distinct parabola. If you were given the vertex, then you can determine the equation of the parabola with just 1 more point, but that's because that vertex actually gives you additional information. And if you have 1 point on one side, then you have a matching point on the other side. So you really still do have 3 points. So we need 3 points to determine a parabola. Now, what that means in terms of our whole approximation idea, and I'm not going to draw the picture of our ln function necessarily. I'm just going to draw sort of a general thing that we might be trying to figure out the area under. What that means for us, if we break this up into regions, and I'm going to do about 6 regions, I think. So I want to go from here to there. Since we need 3 points, when we break this up, we actually have to pair up our little segments. So in other words, what we're going to do is we're going to find the area under 2 of our subintervals at a time, because we've got 1, 2, 3 points, and we could find the area under there. And then we're going to pair up again, and for the second piece, let's use a different color. We're going to use those 2, and we would use that point again, and that point, and that point. And then for our last grouping, we're going to go here. Actually, let's do this. And we're going to use this point, and this point. So that means that for Simpson's rule, if we have 6 subintervals, it's really 3 parabolas. If we had 20 subintervals, it's 10 parabolas. If we had 9 subintervals, we'd have a little problem because we'd have 4.5 parabolas, and we don't want to do that. So when we use Simpson's rule, we're going to insist that n must be an even number. Otherwise, we can't pair these guys off. Okay, so now what we need is the formula for the area under a parabola. And we're not going to go through and argue about this or fight about this. You guys can go look it up if you want to find the formula, but here's what it looks like. The area under a parabola through 3 points, and we're going to label them y sub 0, y sub 1, and y sub 2 for this first one, is the first y value plus 4 times the second y value plus the third y value. And remember how in the trapezoidal rule, the area was all of those things divided by 2 because we were somehow averaging them. This is sort of a weighted average, but there are 3 of them. And then what else do we have to consider? We have to consider the height or the distance between those. So that's the area under a parabola. So height over 3 times the first y value plus 4 times the second one plus the third one. So it's kind of a weird formula. You can go look up how to find the area under a parabola and see the development of it. I don't want to take a ton of time here on developing the formula. That's just one piece. So for example, if I label these guys, I'm going to label my points up here: y sub 0, y sub 1, y sub 2, y sub 3, y sub 4, y sub 5, y sub 6. if I label these guys, I should be able to find the area under this entire thing from x sub 0 to x sub 6. And the way that I'm going to do that is I'm going to notice that every one of my parabolas, my parabolic sections, is going to have that h over 3 in it. So I'm going to factor it out to start. And then I'm going to add up my 3 pieces. So my blue one, yeah, Gabe, you have a question.
Yep.
Go ahead.
What are those arrows? You see how you have that formula?
Those arrows were up there when I was talking about the 3 degrees of freedom in the parabolic equation. So those refer to the A, B, and C. There are 3 parameters in there, and that's why we need 3 points to determine a parabola.
Oh, okay. Cool. Thanks. And there's 3 points on that little sketch you have on the very left, the dotted line one, right? Dotted line parabola.
Yes, there are 3 points there.
All right. Thank you.
You're welcome. All right, so my blue parabola, for the blue one, I've already got the 3 pieces, the h over 3 factored out. The blue one is going to be y sub 0 plus 4 times y sub 1 plus y sub 2. And then the height over 3, remember the height is the distance between regions, so that's the height. It's the delta x, if x is our independent variable. Then for the red one, it's going to be y sub 2 plus 4 times y sub 3 plus y sub 4. And finally, for the green one, it's going to be y sub 4 plus 4 times y sub 5 plus y sub 6. And my 6 doesn't look like a 6, so a little bit longer. Y sub 6. That's okay. So now I'm going to add together my like terms, and I get the first y value plus 4 times the next one, 4y sub 1, plus 2y sub 2's. Y sub 2 showed up in 2 different parabolas, so I get 2 of them. Then I get 4y sub 3. It was in that middle piece from the next parabola. And I get 2y sub 4's, also in 2 different parabolas. And 4y sub 5's. And y sub 6 is out there on the end, so I only get 1 of those. Oh my gosh, this thing is behaving badly. All right, good enough. So there's my area formula for Simpson's rule with 6 subintervals. Now notice that we could expand this out to 8 or 10 or 20 or however many we want. We just recognize that the terms on the ends get multiplied by 1, and the terms in the middle alternate 4's and 2's. And they have to start and end with 4. If you don't have an even number of subintervals, that won't work. And so that's part of why Simpson's rule insists that we have an even number of subintervals. All right, so let's take that formula and go back and do our log problem with Simpson's rule. We were looking at the integral ln x from 1 to 5, and we were dividing this up into 4 subintervals, so something like that.
After we're done with this page, do you mind going back into the last page we were just on, so I can finish writing down the other stuff?
Not a problem.
Cool. You don't have to do it right now. You can.
Okay. Remember, everything is in the recording, so you can.
Right. Yep. Okay.
Go back and grab it there too.
Sounds good. Thank you.
All right. Did you have another question, Gabe, or was that your hand from that?
Oh, I didn't even mean to raise my hand again.
Okay, all right.
Thank you, though.
Okay, so what we're thinking is essentially it's two parabolas. So one parabola and then a second parabola going through there, through those 3 points. Those 3 points, those 3 points. And you really don't have to draw the parabolas each time. I just want to give you a sense of where they're coming from and where our subintervals are. So how does Simpson's rule work? It says the area is approximately height over 3. So height is 1. 1 unit between values. And then where you're going to use our left-hand endpoint, natural log 1, 4 times the next one, 4 times natural log 2, 2 times the next one, 2 times natural log 3, 4 times the next one, natural log 4, and 1 times the last one, natural log 5. So notice in the middle, those terms alternate with coefficients 4, 2, 4, 2, 4. Actually 4, 2, 4, just 3 of them. And the endpoints have coefficient 1. And so we're going to add up those numbers. And I think I can do this kind of nicely because I typed it into Mathematica so I can copy and paste and then just change the numbers that I need to change. And I get approximately 4.041. Which, if we remember correctly, the calculator, just using integrate on the calculator or Mathematica, gave the actual value of 4.047. So this time we are correct to the 100th place and only off by about 6 1,000ths. So our error is becoming less and less and less as we sort of modify these approximation techniques. Now, one thing to note about approximation techniques is that since we do have calculators to do problems like integral of ln x from 1 to 5, they really aren't extremely handy anymore. Does that make sense? It's sort of like approximation techniques for figuring out square roots. Well, you got a calculator, so if you need the square root of 5, you can hit the square root button on your calculator and figure out that it's 2.2 whatever. So they don't come in very handy there, but they do come in handy in some other types of problems where we don't actually have a function, but we have a bunch of measurements. So we're going to look at that next. Now, Gabe, you wanted me to go back a page, I think.
Yep.
So I think that one is the one you were looking for. Is
Yeah.
that the one you wanted? Okay.
Yep.
I'll leave that one up there and you guys can take a peek at it.
Thank you. Mm-hmm.
All right, I put a PDF in the chat. Merrick, are you seeing it?
Thank you. I'm good if everyone else is good.
All right, Merritt, can you get to that approximation methods thing that I put in the chat or no? Okay, I'm going to put it up in that same place with the additional materials from chapter 3. Okay. So it's also in e-learning for you, Merrick, and for everybody. Close that up. Okay, so I think I tried this time. I am gonna quit my share on that, and then I'm gonna share, I think I can share screen now. For some reason, it seems to be working again. Okay. So you should have this approximation methods handout on your screen. And it looks like you do. Good. So rectangles or Riemann sums were the method we looked at first. Then we looked at trapezoids, and the trapezoidal rule is there for you in all of its glory. Remember, f of x values just mean y values. So to approximate with the trapezoidal rule, you need your height, which is your distance between x values. You're going to divide it by 2. That came from the formula for the area of a trapezoid. And then you're going to add up the function values with all of the middle values multiplied by 2. And then Simpson's rule, we're using parabolas, uses this formula for area, height over 3 times y sub 0 plus 4y sub 1 plus y sub 2. And when everything is simplified, you have your h over 3 out in front, and then the alternating 4s and 2s in the middle. So it looks very much like the trapezoidal rule, but the 3 is different, and then the coefficients are different. So we're going to try to do one of these problems, and there's a couple of examples here, but let's just try number 2. Let's try one that's a little bit different. We're going to estimate the integral from -1 to 1 of e to the minus x squared using 4 subintervals, and we're going to use, we'll probably not do all of these. We'll do one of the rectangles, and then we'll do trapezoidal rule, and then we'll do Simpson's rule and sort of compare. Okay, so looking at problem 2. So if you draw a picture of this function, always a good idea, no matter what we're working on. Remember, e to a power is always positive. This graph should look something like that, although a little bit more symmetric than I drew it. Should be symmetric about the y-axis. Notice the minus x squared. Notice when x is 0, the y value is 1, since e to the 0 power is 1. And then as x increases, the y values. So 1 will be out here, -1 will be out here. So when x is 1, the y value is e to the -1 squared, or e to the -1 power. Notice that when you square -1, you get the same thing as when you square +1. So this is also -1 e to the -1 power. And then I'm going to need the x value of 1/2 or 0.5 and the x value of negative 0.5. So this will be 1 e to the minus 0.25, right? Squaring 0.5 gives me 0.25. And squaring negative 0.5 also gives me 0.25. So it's e to the minus 0.25. And you might want to go sort of grab those numbers on a calculator if you just kind of want to visualize what they are. E to the minus 1 power is about 0.37, I think, 0.38, somewhere in there. E to the minus 0.25 is going to be larger than that. So you can estimate those if you wish. So if we've got all those, see if you can set up, let's start with right endpoints. We'll do right endpoints, then we'll do trapezoidal rule, and then we'll do Simpson's rule. So we're going to do those three. So my right endpoints are going to kind of look like this. Notice I'm going to overestimate on this first one, also on the second one, but I'm going to underestimate on the third one and underestimate on the fourth one. So those are my 4 rectangles. Also notice that my delta x is what? Or my h? What's the distance between my points?
0.5.
0.5, yeah. So for B, we're looking at delta x, 0.5, times the sum of all the y values I'm using. So the first one is using right endpoints. I'm using these 4 y values. E to the minus 0.25 plus 1 plus another e to the minus 0.25 plus an e to the minus 1 power. I'm going to go grab my calculator. It's easier than using Mathematica on this one. Hopefully not catch my computer. So e to the minus 0.25. Okay, so I got on that first one, my calculator says, that's approximately 1.46274. So you guys can let me know when you get there if that's what you got. Aaron E, thank you. Okay, I figure if two of us get the same thing up to 5 places after the decimal, we're probably pretty good. Then let's try D. We'll use a different color. We'll try D. So D is trapezoids. And so I have to use all my values. We're going, here's one. Here's another one.
I got what you got too for B.
Good, good, Gabe. So something like that. And it looks like there's some symmetry in this graph. So I should have the same amount for my left and right ends and my middle ends. Excuse me. Oh, but let's go ahead and let's see if the formula can work for us. H over 2, so 0.5 over 2 this time. Now, left endpoint plus 2 times the next endpoint, e to the minus 0.25, plus 2 times the next one, 2 times 1, plus 2 times e to the minus 0.25 again, and then e to the minus 1. And so I could type all those in, or I could use the symmetry to sort of decrease a little bit on what I have to type. But let's see what I get. So I'm going to go in here. I've got 0.5. I need to divide that by 2. Divided by 2. Okay. Then times. So I see 2 times e to the minus 1 in parentheses. And I see 2 times 1. And I see 2 or 4 times e to the minus 0.25. So let's make that 4. And delete all of this. And I got the exact same thing I had before, at least up to those 5 decimal places. You guys are the same. Okay, cool. And then finally, the last one, let's use another color. We'll go this funky purple because I think it'll be easy to see. So we're using parabolic segments. Essentially, it's using 2 parabolas. So this time I want h over 3, and then left endpoint, and the 2's, that 2 changes to a 4. That 2 stays a 2. That 2 changes to a 4. And the last term stays the same. So I should be able to enter there. And so I have 2 e to the minus 1, 8 e to the minus 0.25, and then divided by 3 instead. Oops. By 3 instead. And I get 1.49436. 1.49436. Did you guys get that? I might need to give you another minute to get that typed in. Thanks, Aaron. And Aaron, the Aarons agree. And if we go off to our calculator or Mathematica or whatever and just use our integrate function, let's see, integrate from -1 to 1, e to the minus x squared dx. My calculator says this. So let's see,
I got that too.
I didn't use green. So calculator, just using the integrate function, says 1.49365. So this is really quite good, because if we were to round each of those to the nearest thousandth, they agree. So our error is less than 0.001 in using Simpson's rule.
So can you explain you may have already said this, but can you explain the significance of using Simpson's rule versus using a calculator?
So, okay, so in this scenario, obviously the calculator is truly using approximation techniques, but it's got it so embedded in that integration that it's able to get much, much closer. So, but what Simpson's rule is going to do for you is that it's going to allow you, in a problem like this, there's no benefit other than the exercise of using an approximation technique. Okay, makes sense? You're stuck on a deserted island, and for whatever reason, you needed to calculate the integral of e to the minus x squared dx, and you didn't have a calculator that would calculate the integral directly, but you did have the ability to compute e to the minus 0.25 power. Okay, that's pretty ridiculous, right? Because
Right.
you do one calculation but not the other, so kind of hokey. Where these rules come into play, where they become much more useful, will be seen in the next problem we do, where we don't have a function. Okay, and we just want to sort of estimate something. So let's
So if we didn't have a calculator, then we could still calculate
well,
all this
I mean,
stuff?
so could you do those three calculations that I did in B, D, and E without a calculator?
No.
No. You could write out some things. You could maybe do some decent estimating if you thought about them, but you could not theoretically do that with any too much degree of accuracy without a calculator. However, let's take a peek ahead and look at where the approximation techniques will come in very handy. So I'm going to jump us up to the next problem. And let's see if we can read this and see what's going on. So we want to construct a straight level road that's 600 feet long and 75 feet wide by making a vertical cut through an intervening hill. The heights of the hill above the center line of the road, as obtained from a contour map, are as follows. So, so we've got this road, and we've got this funky hill, and so I'm just going to draw a graph of the hill itself. That one's pretty straight. All right, so at 0 feet from the center line, or at the 0 foot level, we are a height of 0 feet. At 100 feet, so our scaling is 100, 200, 300, 400, 500, 600. Just draw a nice little graph of what's going on here. And what's our largest height? Our largest height is 25. So I'm going to go 5, 10, 15, 20, 25. And that's at the 400 foot mark. And at the 100 foot mark, we are 7 feet high. At the 200 foot mark, we're at 16. At 300, we're almost to the top, almost 24. At 500, we're back down to 16. And at 600, we're back down to 0. So we've essentially got this funky hill, and we want to cut through it. And the region that we're cutting through, so it's kind of a sketch of some function. the region that we're cutting through is 75 feet wide and the 600 feet long. Notice we've got the 600 feet accounted for in the drawing. So picture this parabolic section extending backward or forward, if you like, for 75 feet. So this comes back, and I can't draw another parallel region like it, but I'm just going to draw the one side. And you got this sort of mound. It's not actually all that bad that we're cutting through. Does that make sense? Okay. Thanks, Merrick. Thank you. Thanks, Aaron.
Kind of.
All right, so we're trying to chop through this dirt. In order to figure out, let's see what they asked. They want to know how much earth we're actually moving. So we're moving all of the earth under this thing. We're trying to approximate this volume. And to approximate the volume, what we're going to do is we're going to start by approximating the area under the curve. And then multiplying by the depth of this hill that we have to get through, the 75 feet, and we will have the volume of dirt to be moved. So how do we get the area under the curve? We're going to use an approximation. And we can approximate. Notice that I did not say anywhere in here that you have to use trapezoidal rule or that you have to use Simpson's rule. We could do it with both. Let's go ahead and use Simpson's rule just for practice with it, since it's a little bit funkier. So what does Simpson's rule say for our area? Well, it says the blue area should be h/3 times the first y value plus alternating 4 times the next one, 2 times the next one, 4 times the next one, 2 times the fourth, 4 times the fifth, and then y/6. Notice there are 7 y values, so 6 subintervals. The height is the distance between those measurements. And so the height is just that 100 feet. And I'm going to put my units in here so we can note that they do make sense. And the y values are just the y values that were given in the chart. So they are the 0, 4 times y/1, 4 times 7, 2 times the next one, 4 times the next one, 2 times the next one, 2 times 25, 4 times 16, and then the end, we had that 0 again. Notice that all of these measurements, I didn't write them in, are in feet. So when I add up all that stuff inside the parentheses, I'm getting feet. I'm multiplying by feet, so my answer is going to be a certain number of square feet. And this I could do on a deserted island without a calculator. I'm probably going to use one here anyway, but I could do this without a calculator. And I get times 100, 3, I get 9,000 square feet. Thanks, Aaron. Good. We concur. So that's the area of sort of the face of this hill that we've got to chop through. But now to get the volume, we have to take that one step further and do what with the 9,000 square feet? We're going to multiply it by the 75 feet wide. So times 75 is 675,000 cubic feet. And if you wanted to, you could of course convert that to cubic yards or some other unit that you might need. So that's really the scenario where these approximation techniques come in more handy, because we don't have a function for the points running through the curve. Although I suppose we could go and use some sort of regression and try to approximate the curve with, you know, maybe a quadratic function or maybe a cubic function or something like that.
What do you mean by regression?
So you should have worked on like a linear regression where you find, say, a line of best fit, maybe.
Yeah. And
So you could find the parabola of best fit or the cubic function of best fit, and then you could integrate that function instead of using the approximation technique. But this is kind of straightforward and something we can do on a desert island without a calculator. Okay, so that's what I've got for today. I'm not gonna, I think we did enough problems with the, just sort of the basic formulas, and then we did a problem here with the application. Do you guys have any questions?
I do.
What is your question?
Actually, never mind. I remember. Never mind. I don't have the question anymore because you already answered it last.
Okay. All right. Very good. You guys good? Caitlin, Merrick?
Yeah, I'm doing good. Thank you.
All right, good. I think we should be good for today. I will see everybody on Monday. I should have more. What's the date today? Today's the 14th.
14th. Yep.
So, and this is week 7 already. I can't believe it.
That's crazy. When do you think the midterm will be released? Like when will
it's going to be ready on the schedule that I had, which my printed copy is.
You said the 25th. That's what I saw.
I think it said, that sounds right. Let's see.
I said we were taking it to 25th. I can't remember. I thought we were taking it like 26 or all the way up to like 27th. I mean,
I think I feel like I said the 26th to the 29th. And Word is taking forever to open because I just updated it. So it's like time to play the Jeopardy theme song while we wait.
That's okay. Is it posted in e-learning?
Yeah, it's on the schedule. I think that it's what's in my memory is the 26th to the 29th is the window. So
okay, that's fine.
Have it up there at the beginning of the window, and then you'll have through the end of the window to complete it and then upload your work. So you won't have to like hurry to try to do it. There's no time.
Like time.
Yeah, so you don't have to like, print it and do it in 2 hours or 3 hours or something like that. You can just print it and do it, and you have that window of opportunity to work on it. Oh, there it is. Let's see. It says Yeah, I had Monday the 26th through Thursday the 29th. That's correct.
Okay,
Sounds
perfect.
good.
Thank you.
And then your next test window, your Alta, your test number 4 is due on the 25th. So it's due just
Okay.
before that. I was trying to make those not overlap.
Oh, I think I was talking about the 20. Think I was talking about that test actually.
Right. Okay, so that one is due the 25th.
Okay.
All
And
right.
that's a Sunday, right?
That is a Sunday, just like all the others have been.
Okay. Yeah, but I just wanted to make sure it didn't change because the midterm was right after it.
Okay. Nope, it didn't.
Will we have class Monday?
We will, and we'll probably talk about new things. So.
That won't be on the midterm. I'm talking about like Monday, like the 26th.
Right. Yes, we
Oh,
will.
okay. Thank you.
Okay. All right. You guys all have a great day.
You too. Thank you.
You too. Take care. Have a good weekend.
Yeah. You
Have a
too.
good weekend, everyone.